The Hadean Eon, dating from about 4.5 to 4 billion years ago, marks the earliest geological period of Earth's history. This period is named after Hades, the ancient Greek god of the underworld, reflecting the harsh conditions on the primitive Earth. During the Hadean, the planet was predominantly molten, with extensive volcanic activity and a surface continuously reshaped by the cooling of molten rock. There was no life, and the atmosphere was likely composed of heavy gases such as methane, ammonia, and carbon dioxide. As Earth entered the Archean period around 4 billion years ago, it began to cool significantly from its initially molten state. During this time, water vapor released from continuous volcanic eruptions condensed to form the first oceans. This gradual accumulation of water transformed the previously rugged and volcanic landscape into vast, expansive water masses. These early oceans played a crucial role in further cooling the planet's surface, creating a new, predominantly aquatic environment devoid of life, and setting the stage for the planet's evolving geology. During the early Archean period, around 3.5 billion years ago, Earth's crust had cooled enough to form shallow pools and basins on land. These basins collected water, resulting from the condensation of volcanic steam, and mixed with chemicals from volcanic gases such as methane, ammonia, and hydrogen, creating a primordial soup. Energized by sunlight, lightning, and volcanic heat, the chemical-filled pools on early Earth facilitated the creation of amino acids. These simple molecules gradually linked together, forming more complex structures in the primordial soup. Over time, these structures evolved into the first simple cells, marking the beginnings of life on Earth. Cyanobacteria, also known as blue-green algae, emerged around 3.5 billion years ago during the Archean period. These early single-celled organisms developed photosynthesis, using sunlight, water, and carbon dioxide to produce oxygen. This process dramatically increased atmospheric oxygen, enabling the evolution of more complex life forms. Cyanobacteria remain prevalent today. They are still essential to many global ecosystems. The oxygen in the atmosphere enabled a completely new step in evolution. The simple cells of the cyanobacteria began to collaborate, forming clusters of cooperating bacteria. In these clusters, each cell developed its own specialization, from energy production to DNA protection and environmental interaction. These larger cells, composed of various smaller cells, are called eukaryote. In the shallow parts of the oceans, 1 billion years ago, something remarkable happened. The eukaryotes discovered these areas and began to work together, forming complex structures. These regions provided abundant sunlight and nutrients, perfect for photosynthesis. As these early seaweeds adapted to their environments, they diversified into various forms, filling the shallow marine areas with a variety of seaweeds that defined the underwater landscapes of that era. Before these seaweeds could evolve into new life forms, around 720 million years ago, disaster struck. Due to an unknown cause, the young Earth began to cool significantly. It became so cold that the ice caps at the North and South poles expanded and covered almost the entire surface. Everything was covered in ice, and the average temperature dropped to minus 50 degrees Celsius. This period is known as the Cryogenian, sometimes also referred to as snowball Earth. The deep freezing of the Earth affected both the oceans and the land surface, leading to drastic changes in climate patterns, ocean currents, and the environment. This icy condition would last for 85 million years, exerting extreme selection pressure on all life forms. In the next episode, we will see how Earth breaks free from the icy grip of the Cryogenian, followed by the Ediacaran period and the Cambrian explosion. Both periods are known for an extraordinary diversity of the most bizarre life forms.